Okay, in this problem, what do we have? In this, I actually worked in a float glass plant after I got out of the Navy. I was a mechanic, electrician, welder, electrical technician. I worked on some very basic robots, troubleshooted a float glass plant. And you know what a float glass plant is? How do they make glass? How do they make these big sheets of glass? They put a bunch of raw material in a big furnace, salt, soda ash, dolomite, recycled glass. They put it into a big furnace, a hopper. They mix it up, and then they dump that stuff into a furnace so that the level of molten glass will stay at a certain level. And then as they put new material in it, that new material melts and becomes part of that mixture. And then it's maintained at a certain level, so it's constantly pouring out. And the glass pours out like warm taffy, clear warm taffy, onto what's called a tin bath, liquid tin. And then they stretch it. And the more they stretch it, the thinner it gets. So if you need thick glass, you don't stretch it much. But if you need thin glass, like our window glass, you stretch it a lot. And this ribbon of glass is about, I think, 12 feet wide, if I remember right. It's about 12 feet wide of glass. And it floats on top of liquid tin. And it floats on that liquid tin because the tin is at a lower temperature than what is in the furnace. And then as it goes through that liquid tin, it cools off and hardens. And then it leaves the tin bath onto some rollers. And by the time it gets onto the rollers, it's cooled off a lot. And it goes under a bunch of air vents that cool it off even further from below and above. And then it gets to the cold section of the plant where you run a knife and score the glass. You run a knife at an angle so that the cut in the glass is perpendicular. And then these little wheels pop up to snap the glass. Well, as a technician of this float glass plant, I had to wire up a PLC, a programmable logic controller, so that it delivered just the amount of oil on that scored piece of glass, so that when you score the glass and it's warm, if you don't put the oil on it, what will happen is the glass will melt back together. And when you snap it, it'll shatter in a bunch of different pieces. So that you only want just enough oil to keep that score in the glass from disappearing. Because the glass is warm, it'll disappear. So I wired that up, and it actually worked the first time we did it. And so that when those wheels would pop up, it would snap the glass cleanly. That's a float glass plant. That's what inspired this problem. The other thing that's added is broken glass that's being recycled. Okay, so you put it in a furnace that melts the material to fire hot. Clear taffy spills it out into a tin bath, stretched and cooled and hardened. I got to edit this. The glass ribbon is fed onto a bank of rollers. Man, I didn't even read that. I was just going off what I had written during Christmas break. Okay, so random samples of glass are taken from both production lines to check for impurities. Do you want a lot of impurities in the glass? Do you think people are going to be happy if there's impurities in the glass? You're looking out the window and you see some sand in the glass, specks. People aren't going to be very happy, right? So you're going to take some random samples of the glass and you check for impurities. The results are presented down here. How many defectives do you have, Julie, in your sample? In your random sample, how many defectives do you have? Huh? 50? How many defectives do you have in the old production line? How many, what's your count? How many samples did we take? 800? We all got 800, right? So is there an improvement? If you look at the defectives, is there an improvement? The new production line has minus 35. The old production line has 64. Is there an improvement? Is a new production factory? Well, we don't know. Is there going to be a difference? Yeah, there's going to be a difference, right? The question is what? Is the difference significant? we're going to have a difference just because of random sampling, right? Okay, so the underlying statement up here is what? What do you want the new production line to have? You want it to have a lower. Why did you spend $1 billion to build this new production line if it doesn't have a lower defect rate, right? You want the new production line to have a lower defect rate. That's why you built it, right? So that underlying statement is what? Does the phrase, the new production line having a lower defect rate is equals in that statement? If I had said at least, would equals be in that statement if I had said at least? At least. What does at least mean? If you're at least 21, what does it mean? If the drinking age is at least 21, at least 21. The drinking age is at least 21. If I'm 21, can I drink? If I'm 21? In America, the drinking age is at least 21. You have to be at least 21. That means if I'm 21, I can drink. On my birthday, when I'm 21, I can start drinking if I want. I can go to bars and whatnot, right? If I'm 22, the word at least is greater than or equal to, right? What is that most? What's that most? What is the word at most? In order to get this benefit, government benefit, your income can be at most $25,000 a year. What does that most mean, Julia? Can it be 25,000 if it's at most? If it's at most 25,000, can I get the benefit? At most. If I'm making 25,000, I can get it. Because 25,000 is at most 25,000. What if my income is 24,000? Can I get it? I can. It can't be more than 25,000. So at most means less than or equal to. At least means greater than or equal to. So when you see the phrases at most and at least, that involves the equal sign. That would mean that's the null hypothesis. But here, what are we saying? The defect rate has to be what? It doesn't say at most. It says it has to be lower. It has to be lower. That is the alternative hypothesis, right? The alternative hypothesis is what? The defect rate has to be lower than the old defect rate. You all see that? Lower. If it said at most, then it would look like this. Lower means less than, right? Lower. That's the alternative hypothesis. There's no equal sign in that statement, right? Okay. So that is the alternative hypothesis. So the new defect rate minus the old defect rate, that's less than, right? Emmanuel, what's the opposite of less than? What's the opposite of less than? More or equal. So greater than or equal to, right? What kind of test is this, Julia? Why is it one tail? The alternative is pointing in one direction, right? You see that, Emmanuel? The alternative is pointing in the one direction, one tail, one tail test. It's actually a lower tail test. Why is it a lower tail test? Well, it's pointing in the lower direction, right? The numbers to the left are smaller than the numbers to the right. A million's over here, right? Zero's over here. So it's a lower tail test. Okay, so now we got to get the proportions, right? So what I want you to do now is I want you to copy the table with the T from the into sheet 4 of visualized interactive lecture 4 Excel spreadsheet. Whoops. Paste as match destination formatting. Okay. I'm going to word wrap new and old production line. There you go. Okay. I need the sample proportion, right? How do we calculate the sample proportion? How do we calculate the sample proportion? Emmanuel, how do we calculate the sample proportion? We got these two numbers here, right? How do we calculate the proportion of defects? What are we going to divide that by? What are we going to divide by? Divide by the count. Yeah. We have 800 samples, and of those 800 samples, 64 had defects, right? So our defect rate would be 0.08. Is that what you got, Julia? What did you get? Yeah. We want 4 decimal places. So I'm going to copy this one into sample proportion of the old production line. I'm going to copy this one into the sample proportion of the new production line. Hit enter. Hey, what do you know? We got it all right, right? Oh, that's right. Right? Right. You guys get your sample proportions right? Emmanuel, did you get your sample proportions right? Okay. These are kind of like the differences in means, right? You see that? We did these differences in means last time. Now we're doing the differences in proportions. You got it? Yeah. Okay. What's the difference in sample proportions? How do you get the difference in sample? Which one do you want to take first? Look at the alternative hypothesis or the new null hypothesis. What does it say? P new minus P old, right? How do we do that? You take C5 minus what? CB5, right? Check to see if, and should your difference in proportions be negative? Yeah, they should be negative. Does everybody have a negative difference in proportions? What do you got, Emmanuel? You got your new one minus your old one, right? You got it? You got it? Oh, okay. Did you check to see if you got it right in my open math? You got it? Okay. Now, before we do the standard error, we got to do a couple things. In order to get the variance of each proportion, we have to do what? We have to take the portion times 1 minus that proportion. See that? You see that? Let me zoom that in. See what I did there? I'm going to calculate the variance of each proportion. The first thing I have to do is I have to take the proportion minus 1 minus the proportion. Right? See that? I'm taking this minus itself. This right here is the defect rate. This over here is what? The clean rate. What percent? This right here is the percent that are clean samples. These are the percent that are defective. See it? Where is your sample proportion in 5? Is it in 5? Row 5? So now here, variance of each proportion is just B5 times 1 minus B5 with parentheses around the 1 and the minus. Got it? Julie, you got it? Yeah. Okay. You good? All right. So now what we have to do is we have to divide by the count. What's the count? I'm going to click on the cell 800. Click on the cell 800. Don't type 800. Click on the cell that contains 800 for the old production line. You got it? Emmanuel? I'm dividing by B3, the 800. You got it? Okay, hit enter. You're gonna get a really small number, right? Okay, then we're gonna just drag it over here to get the one for the new production line. It might be in scientific notation, so what you can do is you can change it to number. Add some decimal places. Okay, so click on the value under the new production line. What does it have? It should have C5 times 1 minus C5 divided by C3, right? Okay. This is the variance of, when you're coding this problem, a defect would be 1, a non-defective sample would be 0. How many 1s would you have? You'd have 35 1s, right? And the rest would be 0s. Of those 1s and 0s, this is that variance. So, sorry. This would be the variance. This right here is the variance of the sample proportions. How to get the standard error? Of the difference. So to get the standard error of the difference, you do what? You do equal SQRT. Do equal SQRT parentheses, right? Everybody got it? You click on this variance of this variance of the proportion, and you add it to this variance of the proportions. See it? So you're essentially adding those two variances of the proportions, but then you take the square root of that sum, right? You got it? Okay. And that's our standard error. I'm going to change it to 4 decimal places. From this point on, it's the same problem as we did before. From here on out, it's the same exact problem, except it's a one-tailed test, right? Did everybody get the standard error, the difference correct? You got it correct? Yeah. What's the test statistic? What's the test statistic? What was it before? It was the difference, right? It was the difference. Now the difference in proportions, right? The hypothesized value is 0. So you don't need to do minus 0, right? The hypothesized value is what, Emmanuel? Right here. The hypothesized difference is 0. You don't have to do minus 0, right? I mean, you could do this if you wanted. You don't have to do that. You could just do B6, right? So B6 is the difference in proportions, right? Like the difference in means. Divided by what? What do you divide it by? The standard error of the difference, yeah. That's your test statistic. Mine is a negative 3.0177. I got it correct. Did you guys get it correct? What did you do, Emmanuel? You took the difference in proportions right here, right? The difference in proportions. There's just one of them, right? Divided by the standard error. If your difference in proportions is good in myOpen Math, and the difference in your standard error, the difference is good in myOpen Math, then this ratio should be good. Make sure it's at 4 decimal places too. You got it? Okay, now this is what kind of test? What kind of test is this, Julia? A lower tail, right? So what do we need? We need the probability of this being less than 0. See that? But as an upper tail test, you need the probability of this being greater than 0, right? I'm talking about this right here. If this were a one-tailed test and it was an upper tail test, you'd want the Beyonce probability to the left or to the right, right? There's a lower tail test. So you want the probability of this number being less than 0. So the p-value, and it multiplied by 1, right? Why do you multiply by 1? One-tail test, right? So we're going to use equal norm on S. That's the standard normal distribution. Do we use dot dist or do we use dot inverse? Dot INV. We want to know the p-value. What do we do? Dot inverse? Dot dist. Dot dist. Open parenthesis. Right? What number do you click on now? It's asking for what? Z. That's the test statistic. That's my minus 3.0177. And then what do you do? True. This gives you the probability of being less than this negative 3.0177. In my case, right? And the probability is really small. My p-value is 0.0013. What does that mean? My difference in proportions is, that difference is 3 standard deviations below the mean, right? That's pretty small. That's a pretty significant difference, right? That difference is more than 3 standard deviations below 0, right? So that's my, when our p-values are small, the smaller the p-value, the more significant the difference is, right? The more evidence we have in support of the alternative hypothesis, the more evidence against the null, right? Small p-value, right? So at 10% significance, we what? Reject the null. We can actually reject the null. We can't accept the null. We can reject the null, right? And then what do we conclude? Exactly. And that's exactly what we want, right? So what are we going to do with the old production line? Scrap it? No, we'll probably keep it, but we'll sell that glass at a lower price, right, Julia? We have an old production line that has a higher defect rate. We have a new production line that has a lower defect rate. The glass that comes out of our new plant will be our premium glass. The glass that comes out of our old plant will be our what? Discount glass. We'll sell the glass at different prices, probably, right? One's going to be premium and one's going to be basic, right? This happens all the time in business, right?